Okay. So here's the data collected. Now the question is asking us, explain why the student can correctly conclude that the hydrate was heated off a sufficient number of times in the experiment. Question B is asking to use the data above to calculate the total number of moles of water lost when the sample was heated and determine the formula of the hydrated compound. Okay. All right. Now, if we take a look at the data, here's what we got, guys. Let me go ahead and put my marker on. You have the mass of the empty container. Then you have the initial mass of the sample in the container. Okay, so both the containers have the mass here in total. Now, what do we see happening to the mass every time that we heat it? Anybody? The mass decreases. Look, we go from 25.85. After the first heating, we see a drop to 23.98. Then we see a drop again at the second heating to 23.976. Then we see a drop again at 23.997. Now, what this is telling us is here, something is getting lost. Something is lost, right? So we're heating up the sample and we're seeing a decrease in the mass, okay? So what we see from drop to drop is we see that the mass that's being heated away is actually the water, right? As we keep heating it up, and I put that right here, look, as we keep heating it up, right, we see that the drops in mass become less and less significant, right? From 23 to, let me see, right here. Let's do this one real quick. 25.825 minus 23.982, we get a mass or a drop of 1.843 grams. Okay. From here to here, .976, we have a drop in 0.006 grams. Okay. We actually see a slight increase here of 976.001, right? So what this is telling us here, guys, is as we keep heating it, right, and the water disappears, okay, we're going to see a less significant drop in the amount of mass of the water, okay? Does that make sense? Okay, so most of the water has been boiled away. Let me scroll this up a little bit. Okay, question 2 says, calculate the number of moles of the water lost. Okay, so we just figure out how much water we lost. Okay, this is the combined mass of the sample with all of the water minus, I'm going to use this one here because that's the smallest one, right? 0.976. It doesn't matter which one you use. I'll tell you what, just to make it easier on us, we're going to use the last one. Okay. So 25.825 minus 23.977. Okay. That gives me a total loss of 1.848 grams of water lost. Okay. So now we know if we lost this much water, right? If we lost this much water, then we can just convert that amount to moles. I know that water has a molar mass at about 18 grams. Okay, this is just an approximation. You can do the full calculation if you wish. but you can round it up to about 18 grams, okay? So if we have 1.848 grams of water, and I know that 1 mole of water has a mass of 18 grams, then I should end up with 0.1026, well, 1.027 moles of water. Now, if we look at our question up here, our question is to 5 significant figures, right? 5 significant figures. So I'm going to rewrite this as 0.10269 moles of water. Okay. Now, if that doesn't make sense, please speak up. Please speak up. Okay. Ask me a question. All I did was I used the data presented in the question to figure out how much water was lost. With a simple subtraction, we figured out that we lost 1.848 grams of water. And then from there, it was just a simple conversion to convert from grams to moles. Okay. Determine the formula of the hydrated compound. Okay, the hydrated compound. So here we have the formula MgCl2 times N numbers of water. We need to figure out how many waters that is, right? So we can write the formula. So let's take a look here. Let me erase this. All right. MgCl2 and H2O has a total mass of, sorry, I'm just pulling up the question over here, 25.825 grams. This is with water. This is with water. Okay. So if we figured out that we lost 1.848 grams of water, right? MgCl2 minus H2O is going to be the 25.825 grams minus the amount of water that we lost. Right, 825 minus 1.848 should give us a total mass of 23.977. Okay. Now, remember, this is the total mass, right? If we look at the table, we have the mass of the empty container, right? So what we're trying to do is we're trying to figure out how much of the MgCl2 or the magnesium chloride we have. So I'm going to take the total mass, which is the 23.977 minus the mass of the container, which is 22.347. Minus 22. So I have a total mass for MgCl at 1.63 grams of magnesium chloride, right? Okay, you with me so far? Questions? No? So let's figure out how many moles that is. Magnesium chloride, let me do the molar mass real quick. 24.31 plus 35.45 times 2 gives me a total mass of, so 1 mole. Over 95.21. Are people leaving? Is that what's going on here? Give you guys a second to catch up. Let me know if you have any questions. Am I going too fast? Are we good? Okay. Last bit. We're going to take the moles of water. We're going to take that and we're going to get the mole ratio of water to magnesium chloride. So we figured out water was 0.10269 and magnesium chloride was 0.0171. Right. So let me scroll this down a little bit. Let me rewrite this in a way that we can get, so we can understand. Don't worry, I'm going to rewrite it again. Okay. So here's what I got. I got 0.0171 moles of magnesium chloride. Okay. I want to know how many moles of water. So for moles of water, I mean magnesium chloride to n moles of water, right? That's where we're at right now. Multiply this straight across. Did I do that right? Nope. Screw it up. It's the other way. Yeah, no, I was right the first time. Take the ratio here of 0.10269. Okay, and you divide that by 0.0171, you should end up at 6.00, right? Which equals the moles of water. Okay. So basically what we came up with is that N is equal to 6. So your magnesium chloride formula looks like this. Okay. All right. Now you can screenshot this and put it into your notebook, or you can just do it on a paper and then post a picture in there. Yeah. Tell me when, okay? Right here's good. Guys, please ask me questions. Please ask me questions if you don't understand what I'm doing, okay? These are what the review sessions are going to be about. For those of you that are good with the notes, go ahead and scroll down and start working on this problem right here. All right, go and start working on this one. Now, this one's not going to be a free response. This one is a multiple choice. So this one, try and do it without a calculator. Just see if you can eyeball it. Do you still need me to scroll up, Eileen, or are you good? Look, I can scroll up. It's okay. Okay, you guys have this problem in your notebook, so scroll up and start working on that problem. Okay, so it says when a 3.22 gram of sample of an unknown hydrate of sodium sulfate, right? Sodium sulfate is Na2SO4 times XH2O is heated, H2O is driven off. The mass of the anhydrous means no water, no water. Sodium sulfate is 1.42 grams. That's the molar mass. That remains is 1.42 grams. The value of X. What is the value of X in the hydrate? Okay, it's basically what it's asking you. It's asking you to find this, right? So if we know that the sample was 3.22, right, to begin with, and we lost 1.42, right, grams of water, then we just subtract. Right? Scroll down a little bit. So we ended up with 1.80 grams of anhydrous. Anhydrous again means no water. Okay. The mass of the anhydrous molar mass is 142 grams. What that remains is 1.42 grams. Okay. The value of X in the hydrate. Okay. So questions so far? No. So if we can figure out the mass of the water, right? Remember H2O has a molar mass of 18, right? Grams per mole. So the moles of the water is 1.8 times 18, right? Now we do the same thing. We end up with 1.42 divided by 142. .01 moles of the Na. Give or take. This is all simple division, right? Simple division, simple multiplication. So the answer for this one would be D, right? I did this all like they're gonna, so when they give you guys, when they give you guys problems like this, okay, where you can't have a calculator, they're gonna make the numbers so you can do easy division in your head, right? It's just a matter of moving decimal places here and there. The only real subtraction we had to do for this problem was here, right? But that's really not a whole lot, okay? So it's the same principle. They're just gonna ask you in a different way. All right, so please make sure that you're paying attention to how they're asking you guys the questions. Okay. Yeah, a lot of people have been getting kicked out. I don't know what's going on. Either that or they're just leaving. All right, here's the next one. A sample of a compound contains only the elements C, H, and N. It's burned completely in O2 to produce 44.0 grams of CO2 and 45 grams of H2O with some nitrogen dioxide. A possible empirical formula for this would be, and then it gives you the options here. Again, multiple choice questions are not going to give you the opportunity to use a calculator. So you want to make sure you kind of just eyeball it a little bit. Okay. So I want to give you guys a few minutes. I want you guys to take about 2 minutes. Okay. And start this problem. I want to see how you guys go about it. If you guys have questions, like, let me know. I'll start working it out on the board in about 2 minutes. Okay. So carbon dioxide has an approximate molar mass of 44, right? 12 plus 32 is 44. All right. So if I have 44 grams of CO2 and my molar mass is 44, right? Divided by 44 grams per mole, then you're going to end up with about 1 mole of CO2, right? So remember, you can't use a calculator, so they're going to give you numbers that you can just divide like this. Okay, simple. In every mole of CO2, in 1 mole of CO2, right, there's 1 mole of carbon. So if I have 1 mole of CO2, and for every mole of CO2 I have 1 mole of carbon. Since it's a 1-to-1 ratio, then my element is going to have 1 mole of carbon. My compound, right? 1 mole of carbon. So I already know that. I can eliminate these two guys. Does that make sense? Let's do the same thing with water. we have 45 grams of water. Now, guys, this is under the assumption that you guys actually watched the video, okay? Because we kind of went over all this stuff in the video. 45 grams of water, okay? I know that 1 mole of water is 18 grams. I can already tell you that 18 goes into 45, 2.5. We have 2.5 moles of water, right? Simple division. Now we're going to do the same thing we did with the CO2 and the carbon, okay? All we did was we converted the 45 grams of water that they gave us, okay? And we converted that to moles. Okay, so if I have 2.5 moles of water in H2O, right? In 1 mole of H2O, how many moles of hydrogen do we have? We have 2 moles of hydrogen. 2.5 times 2, that gives me 5 moles of hydrogen. So my compound is going to have at least 5 hydrogens. Of the 2 options left, this is the only one. We don't even need to worry about nitrogen, right? Because we've already found the answer. All right. Questions? Okay. Section 1.4 is composition of mixtures. Okay. This is a relatively easy unit. Basically, it breaks down mixtures for you guys. Okay. Remember that a mixture contains more than one pure substance. And in a mixture, you can still discern one substance from another. When you're talking about pure substances, in a pure substance, everything in the mixture, right, is of the exact same type. Okay, so down below we have a couple of examples. Okay, so you can see in the mixture we have 2 distinctly different particles. Okay, this would be considered a mixture because there's 2 different types. If you look at example B would be an example of a pure mixture or a pure substance, because even though they're more complex and they're made up of different individual atoms, all the atoms or all the molecules in the mixture are, in the sample are identical. Okay, so by definition, these are going to be a pure substance. Okay, C is also going to be a pure substance because these are all the same. And then D, of course, is going to be a mixture. Now, all this stuff is here for you, right? But I want to make sure I explain to you why. So that's pretty much it. If all the particles or all the molecules in the given sample are not identical, then by definition, it's a mixture. And if they're all the same, it would be a pure substance. Okay, questions? Okay, all right. So a 2.4 gram sample of a mixture of calcium chloride and sodium chloride is found to contain 0.12 grams of sodium. What is the percent of this sample, or what percent of this sample is sodium chloride? So in this one is worked out for you, okay? Because this is notes. So a 2.4 gram sample of mixture, okay? So the first thing you're gonna do is you're gonna determine the moles of sodium. Okay, we're going to determine the moles of sodium. So expanded, if you have 0.12 grams of sodium, okay, this is the same thing as saying this. 1 mole of sodium is equal to 23.5 0.0 grams sodium. Those cancel, and you end up with 5.22. That's all it is, okay? Times 10 to the negative third, okay? I know when some of you guys see it like this, you're like, oh, wait a minute, what's going on here? But it's the same thing, okay? Once you get the moles of sodium, you determine the mole-to-mole ratio of sodium, how many moles of sodium are in sodium chloride. It's a 1-to-1 ratio, so we end up exactly with the same number again, okay? Find the mass of sodium chloride in the number of moles, right? Using molar mass, we end up with 0.305 grams of sodium chloride. And then if you calculate the percent, you end up at 12.7% sodium chloride is equal to 13% sodium chloride, right? And that's what it's asking you. What is the percent of sodium chloride? Don't worry, we're gonna do one just like this. Just want you guys to kind of look over it to see how it's done first. And then we're gonna do the example on our own. Okay, here's our practice. A 5.0 gram sample mixture of calcium carbonate and silicon dioxide contains 1.5 grams of calcium. What is the percent of calcium carbonate in the mixture? Okay, so we're gonna pretty much do the exact same thing. All right. So we're gonna convert grams calcium to moles. And you'll see why all this means in just a second. So I have 5 grams, 1.5 grams of calcium. I know that 1 mole of calcium has a mass of 40.08. I end up with 0.037. Okay. All I did was convert from grams to moles. Oh, that I was in. All right. I'm going to scroll down a little bit. Now I got to figure out how much space, right, calcium takes up in calcium chloride. So if I have 0.0374 moles of calcium, and for every mole of calcium, in calcium chloride, I'm sorry, that only happens when I'm recording. Where am I? Oh, calcium. I keep saying calcium chloride, but it's calcium carbonate. Okay. In 1 mole of calcium carbonate, there is 1 mole of calcium, right? Because there's no number here. So I get a 1-to-1 ratio. I'm going to end up with 0.0374 moles of calcium carbonate, right? Let's say that this had been Ca2CO3, for example, right? Let's say calcium carbonate would have been like this. In this case, this mole ratio would have changed, guys. It would have been for every 1 mole of calcium carbonate, there's 2 moles of calcium. But that's not the case. It's a 1-to-1 ratio, okay? So you need to remember, it's a mole ratio, and it's not just like it's always going to be the same number again. You with me so far? Okay. Scroll down a little bit. Oh, Still in eraser mode. You know what? Let me turn this off because this only happens when I'm recording. Okay. Okay, so we have 0.0374 moles of calcium carbonate. Let's convert that to grams. Okay, let's convert that to grams. So calcium is, I need the molar mass, right? 40.08 plus 12.011 plus 15.999 times 3. This cancels. Obviously, it's just moving the decimal 2 spaces. Okay, so this is how many grams of calcium carbonate are in the sample, right? So here's what it means. I have a 5-gram sample, right? The whole sample is a mixture of the 2 solutions. It's a mixture of this guy and it's a mixture of this guy. So by being able to determine the amount of calcium, I was able to calculate how much calcium carbonate is in the sample. Are you with me so far? So of the 5 grams that we have, 3.74 of those grams are calcium carbonate. So if I want to figure out what the percent is, I just take that number, the 3.74 of calcium carbonate, and I divide it by the whole sample. You should end up somewhere along the lines of 74.8 or 75%. 75%. Okay. That's the percentage of it. Now, these practice problems in here are for you guys to work these out, like either in review session with me or on your own. Okay. Questions? Okay. Next one says the mass percent of carbon in pure glucose is C6H12O6 and it's 40%. A chemist analyzes an impure sample of glucose and determines that the mass percent of carbon is 38.2%. Which of the following impurities could account for the low mass percent of carbon in the sample? In this case, the answer is water, right? And the only reason I'm going to, well, it's right here actually. It says the impure sample of glucose has a lower percent carbon than pure glucose. Okay, what the hell does that mean? Therefore, the impurity must have a lower percent carbon than pure glucose. Water contains no carbon at all. So if it was present, it would decrease the percent glucose. So water must be correct. Okay, I can read that too. Here's what's happening. You have a molecule that is carbon, hydrogen, and oxygen, okay? Carbon represents 40% of this molecule, right? But upon analysis, the 40% actually decreased to 38%. So it's a decrease, right? If you have a percent of a molecule or a percent of anything, right? Then what has to happen then is to bring the carbon down, then you have to bring up the hydrogen or the oxygen, right? In terms of overall percentage. If you increase carbon and hydrogen and oxygen, right? Then what's going to happen is you're going to also see either a steady in the carbon or an increase in the carbon depending on how much you add. All of these guys here increase carbon, right? They increase the carbon. So if that was to be an impurity, then you would see an increase or a steady in carbon, but you would not see a decrease. The only molecule or the only compound here that has an increase in hydrogen and oxygen, but not in carbon, is water, right? That's why the answer for this question is water. Okay, here's a little bit more notes for you guys. What time is it? It's 1:17. Okay, I'm gonna go ahead and stop here. I'll finish this up for you guys. We didn't really get that far, man. We only got like 1.3, 1.4. Okay. Let me go ahead and stop recording.